So our first speaker is Stephen Hore. Probably doesn't need much introduction. He's been at the survey, I think, since the late 90s, and is a well-known field geologist, particularly in areas of the Flinders Ranges and Arkaroola and Mount Painter particularly. Much of his time has been centred on trekking and observing geological Flinders Ranges and the desert plains and the uranium-rich Mount Painter area and the prospects to the east of that. In addition to his own research programs, he provides geological data and knowledge, including field presentations to assist with education, research and localised mineral exploration, and he'll very happily go out in the field with anybody who wants him to go with him, so keep that in mind. So, thank you, Steve.
Forward. Yeah, hello, Steve here. So what I'm going to present today is the work that I've done with Neville Alley. We've done a fair bit of work on the Mesozoic, early Cretaceous, and I will then apply some of that work towards uranium exploration and give a summary. Okay, so last year, 2023, Neville and I launched or released our publication. It was a publication on the work that we'd done on the Mesozoic. It was fairly comprehensive. It turned out from a weekender away, it ended up being a bulletin, so it took 8 years. So I've put the number of pages there really just to show off, to show we did a lot. Volume 1 is the work, Volume 2 is all the data, so it was quite an effort. It was heavily biased towards fieldwork. We visited many sites, we revisited many sites, we had to reassess what we saw, come back with interpretation. We did lithologs, and also we did a lot of palynology, geochron, SEM work, geochem, petrology, and then finally putting it together, an interpretation, and then the bulletins themselves, the publications that all took a little bit of work. This is where the work took place, northern Flinders Ranges in the area of Beverley 4 Mile, in the northwest portion of the Curnamona Craton. General geology there, just to give you an indication, Arkaroola, Beverley 4 Mile and so forth. And the place consists of Mesoproterozoic, felsic igneous and metasediments. And those rocks are highly enriched in uranium and rare earths. So there's heaps of uranium in the area, and that's hence why the lights of Heathgate and so are extracting. This is a uranium radiometrics image, and there I've highlighted in the right-hand side below the word 4 Mile is Parallana Creek. You can show where the uranium-rich sediments are being washed out of the Mesoproterozoic rocks. We'll just move on with the general geology. So I've highlighted there in the brown the Neoproterozoic on the western southern side, and then the rest of the region is made up of the Mesozoic and younger basin sediments, Eromanga Basin, Lake Eyre Basin. The primary part of our work that we did was within the Mesozoic, the early Cretaceous, and then also to point out that uranium is hosted in the sediments of these Mesozoic and younger sediments. Highlighting there the Plano Fault, we'll come back to that a little bit later on. It's a big structure, mantle tapping structure. And also I'll just point out the topography quickly. So we've got the rangeland, the hills, which we walk around. Then we've got the range fronts where you're just looking north along the Plano Fault, and I've just highlighted where the 4 Mile West, 4 Mile East in general terms are in that area, very close to the ranges, very close to the fault. It's a drop kick away, it's not too far. And then the bottom right-hand image is just to show you, that's the Skeleton 2 drill hole, which we looked at. And the white arrow is showing you the hills in the distance. We're about 30 k's away from the highlands there. It's just showing that part of the world. This hot springs. So along the Plano Fault, we've got the Plano hot springs. The waters come out of the ground at about 60 degrees C. Relatively low in uranium, and the the heating of the waters is generated by the decay of the uranium-rich granites. And we'll come back to that in a minute. The work that Neville and I did in Bulletin 57, in the release that we had last year, you can see the dots and also the squares. The dots represent a number of the field sites, and the squares, some of the drill holes that we worked on. It's just showing you that we were on the perimeter or the contacts between the Mesozoic and the Neoprot and the Mesoprot rocks. In the bulletin, there are 72 logs, it's just lithologs, just to give you an idea of the work that was put together. And the lithologs, in general terms, location, if there was geochron, we present it. If there was palynology, we present it. And also fossils and so forth. The thing about, with the locations, with tillite horizons, we were starting to recognise which then built up on the story, the initial story by Neville and Larry Frakes from 2003 with identification of the tillite. We're able to find a lot more of the stellitic horizons as we progressed around the Mesozoic and the highland contact. The tillite horizons have a number of striated or facet or polycid clasts. From there, we were able to determine where and the direction of transport those clasts came, or erratics, and some have travelled up to about 30 kilometres. So we were confident in identifying the source and where they'd been transported from and ending up to. Another part of the work was geochron, so we did a lot of geochron on the Mesozoic, early Cretaceous, and also we did some on a rock within the basement, within the Mesoproterozoic basement, a tillite which had baffled peoples for many years, and from there we were able to get zircons as young as 220 million years old. So it didn't quite fit the Sturt story, and so this is support for our work on the early Cretaceous glaciation. I got no claim to know anything about palynology. Neville spent so much time doing palynology, as we have Liliana in the audience here, so she knows so much about it. But Neville spent so much time doing the palynology, and so this is captured, and it helped with the way that we could present the glacial period with the two glaciations and also a number of other new horizons, sandstone and so forth. So we were confident in what we were doing in regards to the early Cretaceous glaciation. Also with the dates, palynology does have a bit of a span, an age span, but we had that and geochron. So we were able to come up with a fairly interesting story, which is sort of presented here. Also, the time period that we're pretty happy now, that there was a glacial event around 139 to about 120 million years. That's where, in red, Australia was 132 million years ago compared to where it is today. So the eastern part of Australia was within the Antarctic Circle. 132 million years ago, we were joint, but were starting to get away from Antarctica. So we were having a few events happening, as well as the inland sea coming from the north through the Gulf of Carpentaria. So we postulated in regards to the glacial events and how much ice was covering Australia and when. So on the right-hand side, we're showing a postulation, if that's the correct word, of where the ice caps have been, where the inland sea was, and there it's depicted where the rifting between us and Antarctica. And we had a few talks this morning about the Otway Basin. That's within that rifting between us and Antarctica. We also investigated briefly that, and also the Bight Basin and so forth. So what did people think years ago about an early Cretaceous glaciation? Well, it didn't really get a ranking. This is in 1993. It was the best one to help support our discussion. You can see the vertical line. There's Australia. We do have the Sturt, Marinoan and Permian glaciations, but no mention of the Cretaceous. So the work that we've done is support of the initial work of Larry and Neville, but we've really intensified it a lot more, and we have this substantial evidence of this glaciation. And at the moment, with regards to research, Australia, or this part of Australia, provides the only physical evidence of this early Cretaceous glaciation. There are spots in Spain where there are drop stones, and there's glendonites in the Bering Islands to the west of Alaska, but that's not quite physical. So we'll move on now and show how I think this may contribute to uranium exploration. I'll concentrate on where I know in general terms. There are others that have a bit better understanding, but we'll work on the 4 Mile, and then I'll briefly discuss the Big Lake area. So shortly after Heathgate and friends found 4 Mile, suggestions came out as to how 4 Mile formed. It could have formed from waters from the Kadnawi Formation. It could have formed from waters percolating down the uranium-rich Mesoproterozoic basement and then coming up fault structures. It could have come through meteoric waters coming off the uranium-rich basement, or it could have been all of them. The Kadnawi contribution was quickly eliminated, and a lot of chemistry was helping support that. The second suggestion was a great suggestion, waters percolating down through the basement and then coming up through the fault structures. I mentioned, I showed Paralana Fault, I also the hot springs, which only had 0.07 parts per billion uranium. It didn't quite work. Roger Skirrow did some modelling. He did a lot of work, and he did a terrific presentation and papers. The fact that percolating waters through uranium-rich granites and then coming up through convection doesn't quite work. When it goes down depth, it's in a reducing zone. When waters oxidise, it leaves the uranium behind. So that didn't quite work. So that leaves the third suggestion about meteoric waters coming off the basement. Here on the left-hand side, we've got a sort of an oblique image of the Mount Painter area. You can just see how much uranium is being drained off the basement. So that's not a bad idea. Roger Skirrow also thought that wasn't the best way for 4 Mile, because 4 Mile is so close to the ranges, it doesn't quite work. So what else may help? So later work on the right-hand side, I've shown where Heathgate have presented interceptions with their drilling on 4 Mile West and the areas. They've got, I can't read it, can I? No? How am I going to go? Oh. So they've got a 4 Mile diamictite on the northern side and the 4 Mile basal conglomerate to the south. So they're up to 60 metres thick. So the suggestion here is that these are part of the glacial event, where rocks have been pulverised and then transported out into the plains and become part of the sedimentary deposition environment in the Mesozoic. On the right-hand side, there's images. The yellow circles will represent a person standing to show you the thickness and the events that happen during a glacial event. So glacial sediments are adding material which then can be added to the uranium budget. So maybe, it's great to be near a terrain that's full of uranium, but maybe just having a little bit of mechanical disintegration and contribution might also help. Also might help in regards to glacial events is the periglacial or the permafrost. There's an image here which shows the range front. It also shows the granites which have been completely altered to kaolinite. The weathering process that happens in some circumstances in glacial events. I'm not saying that this particular location here is a result of glaciation, but it's just showing that areas of the granites can be completely altered and susceptible to weathering. An outcrop nearby in that photograph. All right, I want to move on now quickly to Cooper Basin, the Big Lake area. And the reason being, this image here is you can see how hot my painter is. The top right dot is where Alligator Energy had their recent intercept in the Paleogene. I'm not going to talk about that, but I'm going to talk about what's below that. So 3 kilometres below is the Big Lake Sweet Granite, another hot granite. That was intruded into the Warburton Basin, and due to events of the day, it was uplifted quite rapidly and exposed to events during the Permian and created what's called the granite wash there. That granite wash is 80 metres thick. You know, the erosion of this granite and the weathering of this granite possibly has given also another opportunity for uranium-rich granites to contribute to the uranium cycle. I don't know how I'm going to do this so quickly. All right, we'll do it quicker. So Sebash Jarith from GA Australia, he put out this image in 2008 which shows felsic magmatism and basins, and the reason for that was hydrocarbons and uranium to get that going. What I'll do, put on top of that, is that 132 MA glacial event. Not saying that all these felsic granites and all these basins existed at 132 and then this 132 ice cap. So I'm saying that this 132 ice cap is an example of what can happen to our environment on any given time. So if we substitute Permian or we substitute neoprot glaciation, it's understanding that these glacial events can affect and contribute. Summary, enjoy that. And we'll go back. There was a diagram done by Sebastian in 2008, Alligator Energy updated it, and then I've updated it with the waffle that you've heard and the bits that you didn't hear, but you'll find out what's going on reading that. All bodies stick out of the ground, glaciers come along, all things sort of happen, and thank you. We'll do that. Yeah. Sorry, Liz.